you're going to have to forgive me for if some of my questions sound ignorant. Okay. They're just coming from a place of curiosity. Okay. And I'm trying to help my listeners. I'm assuming all my listeners are somewhat like me in the sense that we don't know some of this stuff that people come on for. So let's break down just quick. What does quantum, right? Does somebody that has no idea, right? What does quantum mean and how do you work with it?
So I'm going to slip out of frame and get a prop
I like it.
because we I think.
I'm all visual, so this is great.
All right, I got all my props. Sorry, I forgot we were gonna actually have to talk about work stuff. I thought it was just gonna be fun,
It is too.
talking about food. I thought we were gonna be in person having lunch, and this is completely not any of my expectation. All right, so let's take this point, right? So 1927, Fifth Solvay Conference, Einstein and Schrodinger and all the famous physicists that you hear about that have been popularized, they get together and the whole quantum mechanics thing comes into play, right? Super, very condensed version. Years and years and years later, 55 years roughly, Richard Feynman and the team decide that you could use a particle as a bit in a computer, okay? Theoretically. All right, fast forward, it's like 2006, 2007, you get your first couple of machines in that kind of range. And there, MIT did one, before that there was one, but it's just real, it's not going anywhere. And then the reason I got excited, the reason I think your listeners and everybody should be excited is 2017, you go from 17 qubits to 2050 up, to 72 and into the 100 range. So there's this obvious long time and then kind of an inflection point. So what does that mean? What is a quantum computer? Well, it's simple. Our iPhones, the laptops we're talking on right now, recording the show with, they all use this bit system, which means I have a heads and I have a tails. And if I have that bit sitting on a two-dimensional surface, think of it that way. If it's heads up, it's a 1. If it's tails up, it's a 0, right? And so on that plane, it can only be one of those two things. So now take that same coin and think of a qubit as a Bloch sphere, right? Think of it as a particle you've popped off, and it's a sphere. So if it's pointing directly up, it's a 1. If it's pointing directly down, it's a 0, depending on how they've designed the system or whatever. And so what does that mean? That means we take that same coin, we flip it in the air. And when we're flipping it in the air like that, is it a 1 or a 0 when you see it spinning? And the answer is you don't know. It's in a superposition of a probability of 1 or 0. And until we stop it and measure it, we don't know what it is, right? And so when you think about it that way, you can take it, this kind of very complicated subject, and make it a little bit more understanding, because you're like, okay, that means that a bit has so many states. You have a 4-bit system, and here's how many outcomes you can have, and it can be in one of those positions at one time. But with a qubit, you can have every time we add a bit, we get 2 to the n the number of bits, and it can be in multiple states or all of the states at the same time. And so then we measure it, that state collapses, and you get an answer that ends up being a 1 or 0. But how you got to that answer means you can go over potentially mass amounts of data faster and very complicated calculations, and they're not going to be good for everything. Quantum computers are not here to replace classical computers. The way I like to think about it is this.
Okay.
It used to take 6 weeks, several months maybe, to cross from New York to San Francisco. Okay? 100%. Or for your viewers, New York to San Francisco. and when you look at that, most of your party died. Maybe you had to eat somebody along the way. It was weird, right? And then the train came along, and it took a week to do that trip. But no matter how far you go, eventually you reach an ocean, right? And so what comes into play? Air travel. So air travel didn't replace train travel. It augmented it for doing a thing that was far more complex, right? Flight is way more complex than, there's wheels on rails.
Sure.
But it served the same purpose, which is it got us to a point. And the point we want to get to is there's a whole class of problems, environmental problems, health-related problems, drug discovery, everything, material sciences to go to Mars. Elon wants to go to Mars. It's like, well, there's going to be a lot of stuff we got to build to get there, right? And this is why, space programs and deep tech is so important to the world, right? We don't think about the Apollo missions and then, all the stuff that we got from that, right, that we use today. But when you think about those problems, they're problems in where the evaluation time goes, you add a few variables, the evaluation time soars. So a classic example is traveling salesperson people like to use, right? It's, I don't think the best example, but for the purpose of the listeners and us, people who aren't quantum physicists, we will get it, right? And that's that we want to go to 14 cities, you and I in Texas. We use my laptop and we calculate all the variables, the possible routes. It takes about 1,600 seconds. Now we want to go to 22 cities, a difference of only 8. But that same laptop would take 2,000 years. And if we went to 28 cities, it would take longer than the time of the known universe. So it's not that computers can't solve some of these problems. It's that it would take tens, dozens, hundreds, thousands, millions of years for you to get to an answer. And that answer may not be right. So think of quantum computing being faster, not like making this video play on the internet smoother or, you know, playing your video game faster, but think of it for that one very specific case, which is there's only certain problems it will be good for, but those problems happen to be things that will completely change the human condition and humanity in general, right? So they're very important.
Yes. Yes.
Does that help? A little bit long-winded, but hopefully that's. And the short version is go buy Quantum Computing for Babies. And you can read it. And it starts off with, this is a ball. It can be red or blue. So if you got that, this book can give you the basics and help you understand it.
So glad you made that book. Look at that's exactly, I need every subject laid out like that. You know, like it just.
Well, my co-author on it, Chris Ferries, has a whole series about all kind of subjects. It's amazing. It started as a joke. I was like, hey, man, we should do quantum computing for babies, right? And I feel so lucky to have done it because now it's like one of the best-selling books in quantum, and everywhere we go, like we literally go meet customers or go to conferences or even virtually yesterday on the event. People are like, oh, you know, I really like that book. And it's funny now because investors that are interested in it have been buying that book, not because of us or anything. And so often we'll be meeting with investors and like, you know, I have the book. And you're just like, oh, you know, we can send you a free copy if you give us money. No, I'm just kidding.
Hey, that's what I would be saying too.
Yeah, exactly.
Y'all could have a book just like this, right? Like, exactly. I love it. No, that's phenomenal.
I wanted to say to the greatest venture capitalist on earth because I have a Sharpie. Do you have a check?
Yeah.